Hello everyone, welcome to my channel. Welcome to an exciting journey into the world of convolutional neural networks, where pixels pave the path to groundbreaking discoveries. I'm Rohit Gowda from Sri Venkateswara College of Engineering. Today I'll be discussing convolutional neural network. Imagine a digital brain, meticulously trained to decipher the complex nuances of images, mimicking the intricate workings of human visual system. That's precisely what CNN embodies. A powerful house or a powerhouse of artificial intelligence engineered to revolutionize image recognition, object detection, and even medical diagnosis. At its core, a CNN operates on the principle of convolution. A convolution, a mathematical operation that allows the network to extract features from raw pixel data. This is what a convolution is. Just like the human brain identifies edges, shapes, and patterns to recognize objects, a CNN sifts through layers of convolutional filters, progressively learning hierarchical representation of visual information. It's akin to peeling back layers of abstraction to unveil the essence of an image. But what sets CNN apart is their ability to learn these features autonomously through a process known as deep learning. With vast amounts of labeled data, coupled with the magic of backpropagation, CNNs refine their parameters iteratively, fine-tuning their understanding of visual world with unparalleled or unmatched accuracy. From self-driving cars navigating bustling streets to medical imaging systems where detecting anomalies invisible to human eyes, CNNs are the unsung heroes behind countless technology marvels. Their versatility knows no bonds, transcending traditional boundaries to leave an indelible mark on fields ranging from astronomy to agriculture. So join me on this exploration into the heat of convolutional neural network. Together we'll unravel the mysteries of deep learning, unlock a world where pixels speak volumes, innovation knows no limit. So let's get started. So, introduction to convolutional neural network architecture. Convolutional neural networks are a type of deep learning neural networks designed for processing structured grid data such as images, etc. CNNs are widely used in computer vision tasks such as image recognition, object detection, and image segregation. The architecture of CNN typically consists of convolution layers, pooling layers, and fully connected layers. Convolution layers are the building blocks of CNN and are responsible for extracting features from input data. Each convolution layer applies a set of filters to the input data to detect patterns and features. The output of convolution layer is called the feature map, which represents the presence of different features in the input data. So this is about convolutional neural network. You can have a look at the layer diagrams here, layer 1, layer 2, and the classifier. So moving on to the convolutional layers. So let's keep this all apart. Let me give you an example for you to understand how convolutional neural networks actually work. Imagine, suppose you're a farmer, standing amidst endless rows of crops, each leaf or a fruit holding the promise of a bountiful harvest or a bountiful harvest. But amidst this abundance lies a challenge. How do you ensure every plant thrives, identifying diseases before they wreak havoc? Here enters convolutional neural networks as your silent guardians. Picture this: drones soaring above your field, capturing high resolution images of every plant with precision. These images fed into a CNN, that is a convolutional neural network, become a digital microscope, scrutinizing each leaf for subtle signs of distress. But here's where the magic unfolds. Through the power of deep learning, the CNN not only identifies patterns associated with diseases, but also predicts their spread with uncanny accuracy. It's like having a team of experts, agronomists at your fingerprints or your fingertips, tirelessly analyzing data to safeguard your crops. With this technology at your disposal, you detect a fungal infection in its infancy. Suppose there is any infection which is not seen to your human eyes. You detect a fungal infancy or a fungal infection in its infancy. Intervening before it ravages your entire harvest. What was once a guessing game now becomes a proactive strategy, ensuring optimal yields while minimizing the use of pesticides. But the marvels of CNNs don't stop here. So let's come to convolutional layers. Convolutional layers, input layers. It's a layers in which we give input to our model. The number of neurons in this layers is equal to the total number of features in our data. Hidden layer. The input from the input from the input layer is then fed to the hidden layers. There can be many hidden layers depending on our model and data size. Each hidden layer can have different number of neurons, which are generally greater than the number of features. The output from each layer is computed by matrix multiplication of the output of the previous layer with learnable weights of that layer, and then by the addition of learnable biases followed by activation function, which makes the network nonlinear. After this comes output layer. The output from the hidden layer is then fed to the logistics function like sigmoid or softmax, which converts the output of each classes into probability score of each class. Moving on to CNN architecture. I'll just explain how a CNN architecture works. Imagine you are trying to teach a computer to recognize different types of animals in pictures. You start by feeding it thousands of labeled images, some of cats, dogs, birds, fish, pigs, etc. Now, let's dive into how a CNN processes the image. First comes convolution layers. Think of these as eyes of networks. Just like how our eyes scan on an image, looking for distinct features, convolutional layers use small filters to scan pixel by pixel, searching for the patterns like edges, textures, or shapes. For example, in a picture of a cat, these filters might detect the edges of its ears, curves of its whiskers. Then comes pooling layers. After the convolutional layers detect features, pooling layers come into play. Imagine this. Imagine this as a way to zoom out and focus on a bigger picture. Pooling layers reduce the dimensity of the features, preserving only the most important information. For instance, if a cat's face is detected, pooling layers helps the network understand its general shape and orientation without getting bogged down by every pixel. Fully connected layers. Now the network has extracted relevant features from the image, but it still needs to understand how these features relate to each other to make final decision. Fully connected layers act as the brain of CNN, analyzing the extracted features, making predictions in our examples. These layers might determine that the combination of pointed ears, whiskers and a triangular nose signifies a cat. Then comes output layers. Finally, the output layers interprets the network's predictions. In our case, it might output the probability of image containing a cat, a dog, a bird or a fish. Now, here's where the magic happens. Throughout the process, where you saw convolution layers, pooling layers, and then fully connected layers, there is something called backpropagation. The CNN compares its predictions to the actual labels of the images and adjusts its internal parameters, like filters like weights, to minimize the difference between the predicted and the actual outcomes. This iterative learning process continues until the CNN becomes remarkably accurate to classify images. So it's an iterative process. So when you show the computer an image of a cat, it's not just seeking pixels, it's recognizing patterns, understanding shapes, making informed decisions, all thanks to power of convolutional neural networks. So this is where the architecture lies. You can just have a look at the image. These are fully connected layers, these are max pooling layers, and these are convolutional layers. Have a look at the image. Moving on. How convolutional layer works. CNNs are trained on a large datasets using backpropagation and gradient descent. The model's performance is evaluated on the separate test set to measure accuracy, generalization, etc. Techniques like data augmentation and transfer learning can enhance the performances of CNN model. A complete convolutional neural network architecture is also known as convents or covnets. A covnets is a sequence of layers. Every layer transforms one volume to another through a differential function. Types of layers. Datasets. Let's take an example by running a covnets on image of dimension 32 x 32 x 3. Input layers It's the layers in which we give input to our model. In CNN, generally the input will be an image or a sequence of images. This layers holds the raw input of the image with width 32, height 32 and depth 3. Convolutional layers. This is the layers which is used to extract the features from the input datasets. It applies a set of learnable filters known as the kernels to the input images. The filters kernels are small matrices, usually 2x2 or 3x3 or 5x5 shape. It slides over the input image data and computes the dot product between the kernel weight and the corresponding input image path. The output of the layer is referred as feature maps. Suppose we use total of 12 filters for this layer. We'll get an output volume of dimension 32 x 32 x 12. So this is how a proper convolutional neural network looks. Here you see activation layer. By adding an activation function to the output of the preceding layer, activation layer adds nonlinearity to the network. It will apply an element-wise activation function to the output of the convolutional layer. Some common activation functions are RELU, max 0 cross x, leaky RELU, etc. The volume remains unchanged, hence output volume will have dimensions 32 cross 12. Next comes pooling layer. This layer is periodically inserted in the coordinates and its main function is to reduce the size of volume, which makes the computation fast, reduces memory and also prevents overfitting. Two common types of pooling layers are max pooling layers and average pooling. If we use max pool with 2x2 filters and stride 2, the resultant volume will be 16 x 16 x 12. So this is how coordinates layers looks like. So what are the advantages of CNN? Good at detecting patterns, features in images, videos and audio signals. Robust in translations, rotation and scaling invariance. End-to-end training, where there is no need of manual feature extraction, and can handle large amount of data, achieve high accuracy. These are the advantages. Moving to disadvantages. Computationally expensive to train, requires a lot of memory. Can be prone to overfitting if not enough data or a proper regularization is used. Requires large amounts of labeled data. Interpretability is limited. It's hard to understand what the network has learned. These are the disadvantages. And coming to some applications in CNN, most of the applications in CNN lies on medical diagnosis, where you